Tell you about experiments we're doing at Princeton on transport of cold atoms in optical lattice systems, simulating Fermi-Hubbard physics. Okay, so the inspiration for these experiments is, or the motivation is to try to understand what's happening in high TC superconductors, which has been, of course, an open challenge for over 30 years now. And in the condensed matter community, there have been a lot of tools that were used to tackle this problem. And the spirit of this talk is that we, in cold atoms, we'd also like kind of to develop a diversity of tools which we can use to study these systems with. So two tools that are particularly relevant for the experiments we do are angle result photoemission spectroscopy. And in the solid state, it has been used to explore, for example, the D-wave symmetry of the gap or the pseudo gap or Fermi arcs, and transport measurements, which again in solid state have been used to discover the superconductivity in the first place, and also to probe the strange metal in the normal phase. Okay, so of course, we're not studying the actual cuprates, we're studying a model of the cuprates, which is the Fermi-Hubbard model. And this is a model that has been studied theoretically for a very long time. And despite all this work on it, we still don't really understand what's happening in the low temperature part of the phase diagram. So the Hamiltonian of the Fermi-Hubbard model describes two species of fermions moving around in an optical lattice, in a lattice. So the realization for us is atoms playing the role of electrons, and they're moving around in an optical lattice. We use two hyperfine states of lithium-6 atoms to play the role of the spin up and the spin down of the electrons. And the atoms can tunnel between nearest neighbor sites on an optical lattice, and they can interact with each other. So if two fermions of opposite spin land on the same site, there's a strong interaction. And we can tune the parameters of this Hamiltonian. So for example, we can tune the tunneling by varying the intensity of the laser beams to control the lattice depth, or we can control the interactions using a tool known as a Feshbach resonance. In the lab, it's just simply changing a magnetic field. So we can vary all the parameters of this Hamiltonian. For example, we can vary the ratio of U over T over orders of magnitude. We can vary the temperature of the system over a very large range. We can also vary the doping. So if we just change the number of atoms in the lattice, that changes the density, and we can think of the system as being hole doped or particle doped. Okay, so the big advance in the last few years with studying Fermi-Hubbard physics with cold atoms has been the introduction of quantum gas microscopy, which gives us the ability to probe these systems down at the single atom level. So you can see in this movie here, this is each one of these dots is a single atom in a square optical lattice. And we can go and probe the system at a single site level, extract things like spin correlations or density correlations, or even more complicated sorts of correlations. Like you could see how the hole, for example, moving around disturbs the antiferromagnet. And there's been a lot of recent activity in measuring these kinds of correlations in quite a few groups now. But this talk is not going to, so these are equal time correlations. So what this talk is going to focus about is really dynamics. So what I want to first show here is the cuprate phase diagram. If we believe the Hubbard model describes the cuprates, then we might expect a very similar phase diagram for the Hubbard model. So we have temperature and doping axes here. So initially, most of the work with cold atoms was at half filling, or in the undoped case. And there we know that at half filling, the parent compound, if you have strong interactions, is the Mott insulator, where the strong interactions suppress density fluctuations. So that's at high temperatures. If you go to even lower temperatures, then you start to have spin ordering and you get antiferromagnetism. So these sort of states we know exist in the Hubbard model from quantum Monte Carlo calculations. And so we can do very accurate quantum Monte Carlo calculations and compare them to the experiments. and use them, for example, for thermometry. We can compare spin correlations, for example, to this Monte Carlo and use that as a thermometer for our systems. Now, if we, so that part is accessible with Monte Carlo because there's no sign problem. Once you start to dope away from half filling, that's where the really interesting stuff happens in the cuprates, but that's also where the Monte Carlo calculations become hard because of the sign problem. So there's several interesting phases in the phase diagram, including the strange metal, which has anomalous transport properties, the pseudo gap, where you have a spectral gap opening up even before the system is superconducting. There's the D-wave superconductor, and there are other interesting phases which are not described in this phase diagram. Okay, so to probe this doped part of the phase diagram, we really need to start probing response functions. And so one tool we've developed over the last year is angle result for the emission spectroscopy in lattice systems. I won't have time to talk about that, but I'll just flash a slide on it. Tom Devereaux will probably maybe mention some work on that because he was a collaborator on the theory side. So here we actually studied the attractive Hubbard model, which does not have a fermion sign problem. So we kind of benchmark our ARPIS technique on the attractive Hubbard model because we can compare to very accurate quantum Monte Carlo calculations. And here, for example, you can see how the gap opens up as you, say, go from the BCS to the BEC regime in the attractive Hubbard system. And our hope is to start extending this technique next to the repulsive Hubbard systems in the doped case, where the calculations are extremely difficult with Monte Carlo. And papers like this from our chair tell us that these dynamical mean field calculations tell us that we're already in an interesting regime of temperature and cold atoms where we're hovering around the temperature regime where one expects to start see the opening of the pseudo gap or changes of the topology of the Fermi surface. So that's where we would like to go next. But let me tell you about the transport experiments we've done so far. And so I'm going to first tell you a story about charge transport, and then I want to move on to a more complicated transport mechanism we've been studying more recently. Okay, so the charge transport, the motivation here for these experiments was to ask the question of whether the Hubbard model has a strange metal in analogy to the one in the cuprates. And surprisingly, this question wasn't addressed very much theoretically. There was some early work with approximate techniques, but nothing with more exact techniques like quantum Monte Carlo. Okay, so to contrast the strange metal, let me first start with a good metal. And there we're assuming we have quasi-particles that carry the various conserved quantities like charge or spin or energy. And these quasi-particles are moving around, they're interacting with each other and colliding every mean free path or so. So now you could ask what happens as you heat up such a quasi-particle system. And what you expect is that the mean free path will start to shrink. And eventually you would expect that it has to saturate at some point because in a quasi-particle system, it doesn't make sense to talk about a mean free path that's smaller than, say, the interparticle spacing or the lattice spacing. So that limit is called the Motiaf-Irregular limit on the mean free path. We can also relate it to a more experimentally relevant quantity, the resistivity. So the resistivity as you heat up the system saturates at the maximum resistivity in a quasi-particle system, which we can call the MIR limit for the resistivity. So another thing we can also say about quasi-particle system is how the resistivity depends on temperature, say in the low temperature regime. The resistivity in a solid state system can, of course, arise to many different mechanisms like disorder or phonons or interactions. Now, the beautiful thing about these cold atom systems is we can really focus on one of these mechanisms because the optical lattices are very clean. They don't have any disorder. And they're rigid, so we don't have any phonons in these optical lattices. So really the only source of resistivity is the interactions. And there the prediction from Fermi liquid theory and from Boltzmann transport theory is that the resistivity should scale quadratically with the temperature. Okay, so that is a good metal. Let's contrast this with what happens in these bad metals. There you have strong interactions which destroy the quasi-particles. And empirically, what's observed in a wide class of materials like the cuprates or the pnictides and many others is that as you heat up the system, the resistivity just keeps going up with the temperature, doesn't seem to saturate, like there's no MIR limit. Also commonly observed in these materials is that the resistivity scales linearly with the temperature. And that's rather poorly understood. And it's hard to, as I said, understand it in a real system because it's hard to isolate what the mechanism responsible for the resistivity. For example, phonons would lead to linear anti-resistivity. And it's hard to say, is there something unconventional going on or is it just simply phonons? So now with the cold atoms, we can focus on the interactions, and there's been a lot of previous work trying to measure resistivity in these cold atom systems. Turns out to be a very challenging problem. Of course, we can't just connect leads to these samples, so we have to come up with more clever techniques to measure the resistivity, and I'm going to give you our take on this problem. So our take is that instead of trying to measure macroscopic quantity like the resistivity, we're going to try to measure a more microscopic quantity, which is the diffusivity, and then try to link this to the resistivity through the Nernst-Einstein relationship. So the Nernst-Einstein relationship tells us that the conductivity, the inverse of the resistivity, is given by the product of two quantities, the diffusivity and the compressibility. So the compressibility is a quantity that cold atom people have known how to measure for quite some time now. The typical way you do it is you put the gas in a harmonic trap. Usually the lattice beams have a Gaussian profile which can be approximated by harmonic confinement near the center of the beam. Is somebody trying to ask a question?
Oh, no, it was just me announcing for later on. Sorry, go on.
Yeah. So we measure the compressibility by putting the gas in a harmonic trap. And if you think about the system in a local density approximation, then this harmonic trap leads to a varying chemical potential, local chemical potential. And simply by measuring the response of the density to that, we can extract the compressibility. So the more challenging thing to measure here is the diffusivity, and that's what our experiments are focusing on. So we wanted to do a clean experiment. So what we did is instead of working with a harmonic trap in these experiments, we worked with a uniform system. The way we achieved that is by sending some extra light onto the sample through the microscope. You can pattern this light using a spatial light modulator, and you can use it to cancel the confinement due to the harmonic trap. So you get a uniform system where we can choose whatever density we want. Here we worked with a whole doping corresponding to about 18% plus minus a few percent. So that's roughly around where this conjectured quantum critical point is in the cuprates. And then what we do is on top of this uniform sample, we add a charge density wave. So we send some extra light through the spatial light modulator in the form of a sinusoidal potential whose wavelength we can vary and load the system adiabatically into this potential. So this leads to these stripes you're seeing in this picture. That's a charge density wave whose wavelength we can control. So that's how we initialize the system. And then what we do is we just simply switch off this pattern, the charge density wave potential, and let this charge density wave evolve within the lattice. And watch how this pattern disappears, okay? So very quickly, we see that this pattern disappears within a few tunneling times, as you can see here, okay? And we can track essentially the amplitude of this charge density wave versus time to learn about the diffusivity of the system. Okay, so let me show you some data here at a strong interaction. So this is U over T roughly 8, and the density, the whole doping is about 18%. And what we observe for a charge density wave with a wavelength of about 5 sites is we observe an underdamped oscillation of the amplitude of the charge density wave. Okay, so this is already surprising, right? That's not what you would expect from diffusion, because diffusion would predict an exponential decay of the amplitude. Okay, so now if we go from a wavelength of 5 sites, let's say, to 10 sites, we observe that the system more damped. And then as we go to 15 sites to 20 sites, it becomes more and more damped, this oscillation. In fact, in the limit of 20 sites, you might think about fitting this to an exponential decay. So that would be consistent with diffusion. So what we're seeing is some sort of crossover going from short to long wavelengths, a crossover between some sort of sound mode where we have underdamped oscillations to a more diffusive behavior at long wavelengths. So to describe what's going on here, we made a hydrodynamic model, a very simple one, where we have these two equations. The first equation is just charge conservation, and the second equation is sort of a modification of Fick's law. So Fick's law is what you would use to describe diffusion. You would say that the current density is proportional to the gradients of the density through the proportionality constant d, the diffusivity. However, that would only give us what the behavior at long wavelengths. And now what we're saying is that these currents cannot build up instantaneously in the system in response to gradients of the density. So we say that the current approaches the steady state value with a current relaxation rate gamma. Okay, so that's the other parameter in this model, how fast the current relaxes to this steady state value given by Fick's law. So these two equations give you, when you combine them together, a second order differential equation for a harmonic oscillator. So that gives you this behavior you saw in the previous slide, where the frequency of the oscillator is given by the wave vector, k, of the charge oscillation, of the charge density wave, and time multiplied by the speed of sound in the system, which would be square root of gamma times d. And the damping rate is just the current relaxation rate for the oscillator. So now we can go and fit these two free parameters, gamma and d, as a function of the wavelength of k. And we find that the model indeed can describe this behavior over different k's with simply two parameters. So this verifies that the hydrodynamics makes sense. So now the interesting thing to do here, and what we've done, is we can study how these things depend on temperature, this gamma and d. And what you see here is the diffusivity goes up as you lower the temperature, and the current relaxation rate goes down, as you might expect, because as you lower the temperature, the Pauli blocking will start to close scattering channels, and so the diffusivity is enhanced. We do observe that the diffusivity tries to saturate at some value, which corresponds to roughly this, Mathiaf-Regel limit for the diffusivity. Okay, so this is one part of the story when you're trying to measure the resistivity, the diffusivity. And we see indeed that there is a non-trivial temperature dependence of this diffusivity. Okay, so the second part is, of course, the thermodynamic quantity, the compressibility. So these are the two things that go into the Nernst-Einstein relation. So we've made measurements of the compressibility the way I described earlier by putting the gas in a harmonic trap and seeing the response of the density. And fortunately there with the compressibility, this is an easy quantity to compute numerically with quantum Monte Carlo, for example. And that's because it's a static quantity, and that agrees very well with the experimental measurements. So one thing to note here about the compressibility is that we're operating in sort of an unconventional regime for condensed matter. So usually you're working at very low temperatures where the compressibility has saturated. It doesn't depend very much on temperature. And any dependence of the resistivity usually would come from some sort of dependence of the diffusivity on temperature. There's another extreme, which is when you work at very high temperatures compared to the bandwidth, which is in our case 8T, 8 times the tunneling. So if you go very high compared to the bandwidth, then the compressibility actually depends on temperature inversely with temperature. That's what you get from the high temperature expansion. So that's this expression here. And the diffusivity saturates. So this combination gives you a linear in temperature resistivity that is well understood once you go to temperatures large compared to the bandwidth. But we're kind of working in this intermediate regime where both the compressibility and the diffusivity are varying with temperature. But what we find is when we take the product of these quantities and take the inverse to get the resistivity, we get a nice line for this doping. Okay, so we again find sort of a linear behavior near this doping of 18%. Now, it does violate the Motiaf-Irego limit, but that's not surprising because as you see from the expression for the compressibility, as you go to infinite temperature, the compressibility goes to 0, so that if the resistivity is expected to go very high. So that part is not surprising, but the linearity is something that's sort of, we don't really understand analytically where it comes from, but we can see it in the data. And we also went and collaborated with various numerical groups to try to see if they can reproduce that result. So we see from finite temperature Lanczos calculations from the group of Yuri Kokolj on a 4x4 site system without any free parameters. They see good agreement with the data. They can't go quite to as low temperatures as the experiment because of the finite size effects that you run into with these calculations. We've also compared to theory from the group of Andre Marie Tremblay, who did single site dynamical mean field theory. That's this green line here, and that doesn't agree as well, but I suspect he'll have some more to say about that in his talk. So after these experiments, there was also quantum Monte Carlo calculations studying, again, the Fermi-Hubbard model close to this doping by the group of Tom Devereaux. And in this beautiful work published in Science, they showed that, again, they can get, with quantum Monte Carlo, a strange metal in a Hubbard model. So, of course, this is a different strange metal from what you have in the cuprates. We're operating in a different temperature regime. In fact, the lowest temperatures we have would correspond sort of to the highest temperatures they have in the cuprates. So we're exploring a different regime where, like most of our temperature range, the cuprates would have already melted. But we're again seeing some sort of linear interresistivity there. Okay, so the next part of this talk, I want to switch from to something very different. Well, we're still going to use the same setup, but what we're going to do now is we're going to add a linear gradient to the Hubbard model. And you'll see that this leads to some very interesting behavior. So let me give you a little bit of motivation for why originally we wanted to do this experiment. So you know that if you're working in a single particle system and you apply a large gradient, then if you don't have any interactions, then you get Bloch oscillations. And you can think of the system in the limit of large gradients as being stark localized. The particles are localized on a single particle level. So there was a couple of papers earlier last year that actually claimed that even in the interacting limit, you would still get some sort of localization in the presence of a clean tilted system. And they kind of drew analogies to many-body localization in disordered systems, saying that here what we've done is we've replaced the Anderson localization in single particle systems with a stark localization, and we've gone to the interacting limit, and again, we're observing some sort of localization up to some critical interaction. Now, that is the point at which we came in with the experiments. We thought, okay, well, that seems to be an easy modification to do in our experiment. Let's try that out. Turns out shortly after we started the experiments, there was subsequent theoretical papers that said these earlier theoretical results were incorrect. Turns out, well, they had started in some particular states that are localized, but if you take a more generic state, it is not localized. So in many-body localization, usually you assume that the whole spectrum is localized. So here it seems there were a large number of localized states, an exponentially large number of localized states in the Hilbert space, but not all, like a generic state would not be localized, it would thermalize. And the reason for that was later understood as some sort of shattering of the Hilbert space into many little sectors, each of which is small enough that it cannot thermalize. And this shattering is due to a combination of charge and dipole conservation in these systems. So this is linked to the physics of fractons that often appears in quantum information. Okay, so, but let me just, that was the motivation. Let me tell you what we did in the experiment. So in the experiment, it's a very similar setup to before. We start with a charge density wave, and we apply a tilt to the Hubbard model. And now the way this is realized experimentally is we just take a large Gaussian laser beam and we sit sort of off center. So we're sitting on a slope of the intensity that provides us with the gradient. Okay, so for some strange reason, my graduate students decided that they would like to align the gradient along one of the lattice axes. So it's a very special case, it turns out, this scenario when you align along one of the lattice axes, because then there are no energetic constraints orthogonal to the gradient, but there are energetic constraints along the gradient. Okay, so basically the fermions are free to tunnel in the vertical directions in this picture, which means that you'll actually get thermalization because now you have a large reservoir along that direction. And to prevent the fermions from tunneling out of the system, we added some hard walls, as you see in these pictures. Okay, so indeed we do observe thermalization of the system. So as we watch versus time, the system eventually goes to some sort of uniform density over some time scale. And the surprising part here to us was how slow the thermalization was. It was actually so slow that in the beginning we thought it was some form of localization we had in the system, but then when we went to very long times, we observed some thermalization. Okay, so let me quantify that. So first, let me show you some data taken in the absence of a gradient. So this is just like before, the same sort of system as before, just going to more moderate interactions, U over T4. And we're looking at long wavelengths of the charge density wave, some anywhere between 10 sites and 25 sites, let's say. We do indeed observe the exponential decays, so this diffusive behavior for long wavelengths that we observed before. And if you fit a relaxation time for this exponential, this relaxation time grows quadratically with the wavelength. So that's what we'd expect from diffusion, right? Okay, so now if we go to a very large gradient, so here I'm talking about this F is the bias between neighboring sites and energy. If the gradient, so let's say a bias is 2 times the tunneling, so it's a very large gradient, we find that the system thermalizes again to remove this charge density wave, but the relaxation time grows like the 4th power of the wavelength. So this is a subdiffusive transport mechanism we're observing here at large gradients, okay? So we tried to understand how this behavior now changes with gradients. So we basically fit our data for the relaxation time to a power law of the wavelength. This power is alpha. And we see a crossover with gradient from the power being 2, that corresponds to diffusion.
You should start wrapping it up because
yeah.
we're going to leave some time for questions.
Yeah. Okay, I'll try to go a little bit faster. So then you go to a subdiffusive behavior in the large gradient limits. Okay, so let me try to explain in the last maybe few minutes what is responsible for this behavior. Okay, so I told you the system starts to thermalize. So the first thing it does is that it actually slips down, as you might expect, it wants to slip down the hill. And so it's exchanging tilt energy with internal energy. But for the system to maximize the entropy, it has to heat up within the single band model to infinite temperature. And there is a finite amount of internal energy you can store. So the system just slips on the order of 1 lattice site to store before it saturates sort of the internal energy in the single band model. So from that point on, we basically conserve the center of mass of the system. And that's what we observe in the experiment. We see a slip on the order of 1 lattice site, and then the system just stays, the center of mass stays the same. Okay, so now we're close to infinite temperature, but we still need to thermalize the system by removing these charge density waves. And the way we do that is, well, so let's think about the system in the gradient when you have an oscillating charge density wave, okay? So there's regions where you have a positive slope of the density. So there you have more density up the gradient than below at low values of the gradient. So that corresponds to a negative local temperature. And then you have other regions where you have a positive local temperature. So we're talking here about near infinite temperatures. So the natural thing to talk about is beta, the inverse temperature. So this inverse temperature is oscillating about 0, okay? And once we figured this out theoretically, we could actually go and measure it in the experiment. So we can measure, say, both the density and the double density and use that as a thermometer. So we can use a high temperature expansion to extract this beta, and we see that it's oscillating. And this is out of phase with the density gradient, okay? So beta is basically proportional to the gradient of the density. Now that you have thermal, you have a varying energy density, you actually need thermal currents to relax the system. So in this last slide, let me just go quickly to how you can get this lambda to the 4 behavior in the limit of large gradients. So basically we're saying we have a heat current that's diffusive. So you have a thermal diffusivity here. So the heat current is proportional to the gradient of the energy. You can, in the high temperature expansion, relate the energy density to beta. So you have the heat current proportional to gradient of beta. And then you just write down the energy conservation and number conservation. So the energy conservation tells you that at every point, the local energy density is related to two things. You can have flow of heat currents, that's this first term here. And you can actually have particle currents. When you move particles down the gradient, you exchange tilt energy with internal energy, so you heat up the system. So that's basically Joule heating. That's the second part here. And in the large gradient limit, it turns out that these, basically whatever particle currents you have heat up the system by converting the tilt energy to non-tilt to internal energy. And then the heat currents carry away this heat. So this E dot in the large limit is actually 0, which tells you that the number currents are related to the gradient of the heat currents, which are related themselves to the gradient of beta. So now you have a second derivative of beta. And beta itself, as you saw before, was related to the gradient of density. So now you have the third derivative of the density. Then if you write down the number conservation, you get an equation that is like n dot is related to the fourth derivative of the density. So that gives you the lambda to the 4 behavior in the large gradient limit. So this allowed us to actually measure the thermal diffusivity. So this thing is actually at this point just depends purely on thermal diffusivity. And so you can measure the thermal diffusivity of the system of this Hubbard model near infinite temperature as a function of the gradient. So as an outlook, what we're trying to do now is to go away from this thermalizing behavior to break the ergodicity by now either going to a 1D system to remove the reservoirs orthogonal to the gradient, or by applying the gradient not along a lattice axis, but along some other direction. Okay, so that concludes my talk. Let me just thank the people who did this work, the graduate students, Peter Brown, Elmer Guardado Sanchez, and Ben Spar, and thank our theory support, in particular, David Hughes at Princeton, and our numerics collaborators, Yuri Kokolj and Andre Marie Tremblay and Tom Devereaux. And thank you very much. Yeah, I'll be happy to take questions.
One question.
I'm sorry, I can't hear you very well. Could you raise your voice?
Yeah, we have time just for one question. Is there any question from the audience here or from the people in the meadows?
I would love to ask a question.
Okay, Antoine.
So, very nice talk, Waseem. Is there any possibility in your experiment to measure frequency-dependent response functions beyond the static transport? Like, you know, perhaps in analogy to some of the things that Joe Tybussin has been doing recently, although at much higher temperature.
Yeah, I mean, it's doable. He's been doing it at higher temperature and I think in a more weakly interacting system. But
also with the trap, also with the parabolic trap.
Yeah. I mean, one can imagine. Yeah, sure. Well, we haven't done it yet, but it could be doable.
It would be very interesting to do in the flat trap.
Yeah, so you want the optical conductivity essentially.
Exactly.
Okay. So with this optimistic note, let's thank the speaker again.